participants, ladies and gentlemen. A very good morning to all of you. I am Shivesh Chandra Bhattacharya, Associate Director working with Advanced Center for Energetic Materials, ACEM, DRDO, Nasik. I am going to present a project on a faster, reliable, digital, non-destructive technique for strategic systems. And with me are present my team members, Ms. Lubna Khan, Sri Umesh Mali, and Navakumar Ghosh. Let me come to the project. ACEM, Advanced Center for Energetic Materials, it is the latest addition to the center, to the number of centers working on the missile systems in DRDO. And it is a state-of-the-art facility in DRDO for the processing of solid propellant, solid rocket propellant, in particularly composite propellant in case-bonded rocket motors. We are situated at Nasik, and that is what I have pointed here in India, in the state of Maharashtra. And this is our administrative and management building at ACEM Nasik, and it is only 11 years old here, and we are working on solid rocket propellant, and we are contributing to the strategic systems of the nation, particularly for SLBMs, submarine launched ballistic missiles, and other missile systems. Now, before coming to the specific activity which I am going to present, let me give you a glimpse of the activities that lead to the processing of a missile, particularly solid rocket motor. It starts with the motor casing. It is an insulated motor casing. Insulation is a nitrile rubber, EPDM rubber that gives thermal protection. Then, in this insulated motor casing, solid rocket propellant slurry is cast. Now, to give a better bonding, good bonding between the insulation and the propellant, we give a kind of paint called, we call it liner. And for that, the insulation surface is generated by upgrading. And in the heart of all this process is the mixing operation. Propellant mixing is the most critical operation that gives you the slurry, propellant slurry, which is to be cast under vacuum or under pressure to give a definite configuration of the propellant grain, and which is giving the ballistics of the missile. Now, in the mixing, there are liquid ingredients, solid ingredients, and basically it consists of binder, oxidizer, some metallic film like aluminum powder, etc. And once the slurry is cast, after that there is a polymerization reaction, we call it curing, and then it turns the slurry into semi-solid and finally solid propellant. And then finally the grain is streamed and finished with inhibition to obtain the required dimension of the propellant grain. Now, up to this, when we are doing the quality control, we can do destructive testing for the raw materials. We do prototype testing, that is also destructive, to determine the mechanical and ballistic properties of the propellant. But at the end of it, before the grain is dispersed or it is taken up for static testing or flight testing, we cannot afford to go for the destructive testing of the grain. So for acceptance, most important part is non-destructive evaluation of the grain. So our project is concerned with this. Now, when we talk about non-destructive testing, it is not only for the final acceptance of a product, it starts with the basic design phase for the material development. And from the non-destructive testing, we can give the feedback to the process stages so that improvement and changes can be made if required. And finally, manufacturing, and the product is accepted. And when it is inducted in service, here, there also for health monitoring, structural health monitoring, NDT can be used. So it is involved in the total life cycle of a project or a product. Now coming to the rocket motor, solid rocket motor, it is considered as a pressure vessel and multi-layered pressure vessel. The outermost layer is the motor casing. It can be a metallic casing of 15 cd6 steel, or it can be a composite material casing like Kevlar or something. Then inside there is insulation. It is nitrile rubber, EPDM rubber, or some other rubber that provides the thermal insulation, and then we get the propellant. So it is so we are most interested in the propellant part, but at the same time we are also interested to find the health of the total system in terms of the interfaces. There are two interfaces, as you can see here, between the propellant and the rubber and the metallic casing. And the thickness of the propellant grain, it varies from 40 millimeter to 1.4 meter or even more. So we are talking about some propellant grain, and here sometimes the metallic casing outside is only metallic, but the propellant is basically a viscoelastic material. And application of NDE to viscoelastic material itself is a critical area. Now, as I have explained the process, now what are the defects we are looking for at the final stage and in the product? Now, during mixing, there are fuel oxidizer, additives, modifiers, etc. And there can be segregation of these liquid and solid phases. There can be solid agglomerates, lump formation, which are not good for the quality of the product. Then during casting, the voids, porosity, and air entrapment, all these things can take place if the vacuum level is not proper and viscosity, temperature are not properly maintained. Then during the polymerization reaction, from the slurry to the slurry stage to the semi-solid, finally the solid state, when the material is transforming, that is the most critical. There, if a big temperature gradient is there, then it will lead to some cracks, which makes the product unsuitable for any application. Then finally, when the grain core or the mandrel is taken out, there may be some damages which may sometimes be repaired, but they have to be detected. Then during machining also some cracks, eccentric waves, all these things can come. And finally some debond, and in between there are gaps or debonds between the interface, that those things can happen. So basically we are talking about material where the casing, if it is a CRMC, that is that composite casing, its density is only 1.7 grams per cc. Insulation density is coming 1.1 gram per cc, around that, and propellant density is 1.75 to 1.8 gram per cc. These are typical values. So you can see that we are talking about of interfaces where the density of the materials are very close, and that requires a very sophisticated system. Now there are two types of modes by which the NDT is done. One is the normal grain scanning. So this is what I am showing here. Here is the high energy source. It can be some X-ray source or linear accelerator or some other source. Then here is the object, and finally there is an imaging device, maybe flat panel detector or film or some system. And for the interfaces, what we do tangential radiography, where this source is aligned in such a way that these X-rays emitted, they are attenuated through the material, through the interface, and the interface information is captured in the film or in the imaging device. Now, coming to the challenges, why we have to go for some innovation and for some new thing. Now, so far I have talked about this NDT technique, which is used for acceptance or evaluation of the solid rocket motors. That is called propellant radiography. That is basically film-based radiography. There, if we go for complete inspection of the propellant grain, it is a Herculean task because of the film size limitation, the huge amount of time that is required, and then we are using for film development hazardous chemicals, then archiving and sharing of the data, that is also not very easy. Now, complete in the inspection of interface, then line-wise inspection if we do, and in different orientation. It is basically a cylindrical grain, so it takes a lot of time, and we have to go for sampling inspection basically. Then continuous remote mode operation we cannot do because of the limitation of the machine. X-ray machines, Linux, we cannot run continuously, and fast processing is also not possible. So these are the limitations of the conventional radiography. And here what I wanted to show you is that the number of exposures required for different sizes of solid rocket motors, SRM, with respect to the probability of detection of a crack or a defect, that improves with the number of orientations when it is increasing. But if we are increasing the number of orientations, the number of exposures also increase, and the time consumed and all this laborious work also is increasing. Now, what is the way out? Now, how to overcome this bottleneck? One is that complete inspection of the problem grain. So instead of radiography, we can go for radiometry. One radioisotope based radiometry, where instead of X-ray, we can take other electromagnetic radiation like gamma. And complete inspection of the interfaces. For that, we can go for non-contact ultrasound testing, confirmation of flaws and checks at the critical areas. For the digital radiography can be done. Continuous remote operations on dedicated manipulator is required. Interpretation of results, dedicated software and data generation for each technique. Now, our solution to this is a radiometry based on radioactive isotope cobalt-60, which is a source of gamma rays, and it is backed with BGO, that is bismuth germanium oxide scintillator-based PMT detector. So here what we get is panoramic radiation that is in 360 degrees. And here we have an array. We have an array of 16 PMT detectors. So these PMT detectors are continuously scanning, and they are aligned with the tip of the. So I come to the schematic of this. So this radioactive isotope is securely stored in a camera. And when we are going to scan this motor, this is the rocket motor, the cylindrical object, and there is a port, and there is a boom going inside the port, and at the end of it only, and that radioisotope is there. And these PMT detectors, they are aligned to the tip of this boom, that is to the radioisotope. And what we get is that, and differential absorption as implicit function of energy, density, and thickness, they are obtained graphically for a given activity of isotope, collimator opening, etc. And we get very qualitative information of the flow. Now, radiometric technique, in short, what we are in our development, in the new technique, what we have done is that we have gone for a radiometry technique instead of radiography, which is suitable for propellant grain inspection. And propellant, as I have told, it is a viscoelastic material. And inspection technique is single wall. See, radiography can be done single wall and double wall. We go for single wall here because the boom is going inside the port. Then source is a cobalt-60 isotope. Detectors are PMT, and output is digital graphical representation. And in normal radiography, we get film-based images, but here we are getting digital graphical representation. And industrial standard for any such detection is 2%, sensitivity is 2%. So that is very much meeting by this method also. It is coming around 1%, 1.2%. So it is highly sensitive, and defect position determination on surface, exact defect location can be marked. Now, once you have conceived this detection technique for a faster, reliable, and sensitive evaluation by non-destructive method of the rocket propellant grain, first what we have to do before we implement it to a real system, we have to go for calibration of this. How do we do the calibration? For that, we take some artificial defects are mounted on the product. They are called image quality indicators. You can see there are some cubes. These cubes can be made of graphite. They can be made of dummy propellant. Here inside we have got the live propellant, and here we are using, which is an explosive material, here we are using dummy propellant, and there are some defects they are mounted. And what we see is that whenever some excess material is there, presence of high density material is there, we get this kind of graphical representation. And whenever there is a flaw or something, then we get a trough in the curve actually. So, and we have seen that from this thing up to 6 millimeter dia for a 1 meter dia product, up to 6 millimeter dia voids can be detected very efficiently by this method. And by the normal radiography with LINAC also, we are achieving almost the same sensitivity. So it is matching. Now, coming to the scalability, reliability, and replicability. Now, as I have told you, see, these are the things we have pasted several IQI, image quality indicators. See some of different types. So there are holes available, and based on that, we are getting this type of patterns. These are basically representation of the attenuation of the gamma ray through the material and with reference to the length of the object. So we are plotting on the x-axis the length of the object. So we know the position here, and this gives the photon counts or the absorption of the X-ray, that attenuation. So from that, what we can see, so you can see these are the troughs. So these are corresponding to some artificially created defects, and based on that, the system is calibrated. Now we go to a real live motor, which is containing explosive material called solid rocket propellant. So then, because of the particular geometry, you can see there are two axis symmetrical slots in it, and there these slots also they have been scanned with these PMT detectors with the by the radiometry, and this is the representation we get, and to ascertain and assess the presence of the slots and if any flaw is there in that. So now, coming to, as I have told you, that NDT is not only used for acceptance of the product and quality control, it is also used for in-service quality control and surveillance. Now, we have some motors for strategic motors, but for the confidentiality reason, I cannot name that motor. So they have been stored for a long time. Particularly these missiles with solid propellants, they are supposed to be stored for 10 to 15 years. So one such motor which was developed, and in the development phase, we have stored it for a long time. And from time to time, we check the health of it. Now, how do we check the health? This is checked by normal radiography to see whether there is any crack developed, any debond is there, or some such thing, or there is some discontinuity in the propellant, in the bulk of the propellant between the solid and the liquid materials, something like that, and which is seen here. But again, if you take any missile, it is consisting of several stages, and an integrated missile is pretty long. And if we have to scan the whole thing by a whole object with the help of this type radiography, anyway, it is taking a lot of time, as I have already explained to you. And then also we are going for sampling inspection, not 100% inspection. The same object we have studied, we have scanned with the help of newly developed this radiometry method, and we have also detected the similar flaws and which refer to the discontinuity. So, and it is much faster and equally sensitive and fully digital. Now, what we look for in a missile system, particularly with respect to the propellant grain, we look for voids, porosity, cracks. In the RT, the conventional method, they are detectable. In the new method, they are also detectable. Then foreign material inclusion, that is a big no-no. So by both the methods, they can be detected. Now, time for completion. Here is the big plus for the new radiometry method. While for a sufficiently mid-size rocket motor to a big rocket motor, large rocket motor, it is usually taking 4 to 5 weeks for radiographic testing. Here it takes less than 2 weeks. Redundancy, it is inbuilt in feature, but here it can be incorporated. Coordinates of defects, here it is coming, it is inbuilt, but in radiography, it is not inbuilt, but it is possible. And production suitability, because there is a machine limit, we cannot run X-ray machines continuously. But here radiometry, it is read with radioisotope, there is no such limitation. So it is fully suitable for the production. Continuous and meant for continuous operation, but the conventional method is not. And manpower requirement also, it is pretty high. Here only 1 or 2 people required. Now, but with all this development, what is the future roadmap? Now, what we get is, we are getting attenuation data and with reference to the coordinate. Now, if we can, if we can develop an imaging software that will map these coordinates with reference to the object, so we can get a 3D picture of this of the object with the flaws indicated. So for that, we are thinking, we are talking of development of imaging software to generate images from gamma ray attenuation data, and development of code for computer tomography of solid rocket motors for characterization of defects. So this will enhance the capability of the system and make it one of its kind for CT without use of costly imaging devices. So part of the our groundwork already we have done. We have already assessed the feasibility of mapping the coordinates to the image of the object. So that part, some work has already been done. On the development of the code for computer tomography that project has been formulated. We are going to take up with some academic institution. So here the important uniqueness of this also is to be noted. It is not requiring any costly imaging devices, which are generally required. Computer tomography, they are basically from radiography, X-ray to CT. These are available in the market. But from radioisotope based, radioisotopes emitting gamma ray, from those radiometry system to computer tomography, it is not yet heard of. So we are going to do that. So here I conclude. So this development, it is a non-conventional, non-destructive test method, and it has been calibrated, tested widely, and it has been implemented in the for the solid rocket propellant systems of strategic programs of DRDO. The radiometry technique using radioisotope, it has been successfully implemented in advanced naval system program. Then, you know, in 2019, there was ACEM missile, their boosters were also cleared, and based on the non-destructive evaluation by this method. And we have also done structural health monitoring, as I have already shown in one of the slides. Let me point here, who are working in India on solid rocket motors. Solid rocket motors are used for space applications and missile applications. So there are ISRO, then DRDO, and ordnance factories. They are the 3 players in this. And in space, as you know, that solid rocket propellant is coming in booster phase, and in upper stages, nowadays, increasingly people are going for liquid propellant and cryogenic propellant. Whereas,
sir, can you please conclude, because we are running out of time?
Yes, sir. Just half a minute. But in missile, solid propellant is the mainstay. And out of all these players in DRDO, this is the young lab ACEM, which is using this thing to very important strategic systems, this newly developed method. And it is fast, reliable, and it generates digital data for online sharing. And we are sharing it to our stakeholders and system labs through DRONA. that is DRDO the online rapid access network, and that is what we are doing, and it compares well with the conventional radiography, as I have already told, and usefulness will be further enhanced if we go for DCT, and this is the first time development in the country, and in the literature also this has not been reported. And these are some of the publications and presentations our team has made. And finally, before I wanted to give you this picture of ACEM, that is Mission Shakti. Here both the boosters were scanned by the new technique. Thank you very much.
Thank you.
Jury members.
I have just a small question. I understand you are using radioactive isotopes inbuilt into the system for ensuring the health of this system. But how it is affecting the users, because it will be causing radioactive hazard?
Yes, sir. I will ask Mrs. Lubna Khan to answer this, my colleague sitting here.
Sir, all these radioisotopes, when they are given by some agency, like in India, it is given by BRC, they are given in some professional cameras. That isotope storage are called cameras. They are designed with depleted uranium material, and the radiation level which is there outside, it is in the permissible limit. So before such facility is commissioned, all these radiation point of view, these clearances are being taken from BRC and BRIC. These are the controlling agencies in India. So all means not only for radioisotope, even if you are having X-ray machine. So the leakage point of view, that safety is of paramount importance. That clearance you have to take first, and then only this operationalization comes next.
My only worry was that when you are storing these motors, motors.
Okay.
And in the motors, you have already inbuilt these isotopes.
No,
so at the
I think actually I just need to give a small clarification. Our isotope facility is different. These motors are brought there, and then this isotope is used to inspect this. So the boom comes and sits in, and then it goes back and sits in the storage. This thing.
In the presentation, it was said. See, in the presentation, it was said that it is inbuilt.
Inbuilt facility for isotope and PMT, but for this
not inbuilt in the motors.
No, absolutely no.
Okay. Thank you.
Yeah.
Thank you.
It's a highly sophisticated system,
right,
and very specialized. And your team is working on this, on the research and all that. Now, when we go for the Atmanirbhar Bharat, how much of this is indigenous?
Ma'am, actually, when we are using such systems, these are use of isotope. It is done in our normal industry also, but we are generating some data. That part is totally indigenous, and the interpretation part and the data generation, this is totally indigenous. Even though this high activity source, it is not presently available in India, so that we had to import. But the rest thing, the arrangement of PMT with this, and the basic technology development, means how these PMTs will be used for the detection, and how this data can be correlated with the flaws in the motor. So this was our own conceptualized
So
idea.
basically the technique, the soft skill is indigenous, and the equipment and the raw material, these are from outside.
Yes, ma'am. Yes.
Okay, so brain is indigenous, the rest is from outside. Right. Very nice.
Thank you, ma'am.
Thank you.
Yeah.